Yeah, myself, I'm Arif. I'm working at CDAC at this point, and yeah, that's about it. Um, Based on my expertise, I would say it's mostly Linux device drivers, low-level programming, little bit of assembly programming, and yeah, I've been working with microcontrollers a lot. So little bit of I think you could say RTOS and bare metal programming, but mostly I've been into device drivers and as well as operating system development. I have also worked with the Yocto project. I've worked on porting Fedora Linux for S5, and I've worked on an IC chip that is custom from CDAC. That is um, there's a 200 gigabit per second NIC for HPC networks, and I think I've worked mostly on that IP over IP stack. Let's see. Secondary skills, as in it would include um, stuff like scripting, automation, um, collaborating using something like Git. So these all like supplement my normal primary skills. Um, like if let's say there's some software suite and that needs manual intervention a lot. For example, I had this Fedora Linux project that was uh, that was having around 30,000 plus packages, and each package had to be compiled for a particular release of Fedora. Then in that case, I just used the Python program to automate all the stuff. I even used a little bit of shell scripting to automate some stuff, and obviously there was use of Git as a version control system. So this was used for versioning packages. So, uh, yeah, normal skills like in Git that would include, let's say, um, mirroring repositories. It would include, let's say, rebasing packages and what is that? Downstreaming distributions and backporting certain stuff that is a little bit more in the newer kernels to an particularly older kernel because when you say, let's say, a chip has been released, the kernel that is being provided by the vendor, it might not be the newest one. They might be using a little older one, let's say an LTS release or something. So regarding that, so I think backporting is one of those things. Um, So again, as I've discussed earlier, so I've worked mostly on low-level stuff, bootstrapping. Let's say, for example, a new chip was released for the 32-bit microcontroller by CDAC. That's a RISC-V based chip. So everything like bootstrapping it from the scratch. That is um, the linker script, the assembly, the startup assembly program, the drivers for that particular chip. So everything from start to the finish, including documentation. So these kind of things are there for let's say the Fedora Linux project. Um, so I had to automate certain packages to be built so that I don't have to manually build everything from by hand. So um, that was using the Python's async.io library. So in that particular project, I had to um, Like basically, I had to maintain lots of network connections. So instead of using the traditional threading methods like multi-threading, I just use I/O multiplexing through select and poll based event loops, and that way I think I sped up the process a lot by a lot. So I think yeah, that's all. I have not really worked with PCI at let's say a programming level. We do use a PCI based card, that is the NIC card, but then again it's all these settings like the address register or the or this endpoints all have these have been configured by my seniors. So I don't really have much like experience with PCI protocol, but yeah, I would love to learn the protocol. So far, I have not exactly configured PCI. Sure. So basically, PCI is sorry. So PCI basically a hybrid of serial and parallel protocol. So usually you use serial protocols due to the complexity, the frequency at which transfers happen. So usually serialization is very great on this, but serial protocols have some limits at like how much data you can transfer at a time. So that's why you use lanes to have to send data parallelly over a serial bus. So that's why I say okay, it's a hybrid uh, protocol. That's a serial plus parallel protocol. So by increasing the number of lanes, you increase the number of um, packets or basically data that you are transferring over the PCI bus. So let's say you have a PCI cross one connection. That means you only have one lane. Then you might be limited to, let's say, according to generation, let's say 1 gigabit per second connection. But you have when you have two lanes, you literally double the speeds. So it is much more similar to it's very similar to let's say the SPI protocol. Not saying SPI and PCIe are similar, but the, the same way we increase the number of data lanes on SPI. Well, you have a dual SPI, quad SPI. So similar way, lanes increase the transfer speeds for a particular generation of PCIe. So let's say I will use an example. I think the most prominent use of PCIe based devices would I would say for me at least that's a video card. That's a graphics card that we use in for video rendering for games and everything. So when you have when you have a card that does not have a very high bandwidth, typically you would have like 192 gigabit per second or something like that. So when you don't have very high bandwidth, you don't need so many PCIe lanes. So you would find cards that are using, let's say, 8 lanes of PCIe. And when, let's say, you are using a SSD that does not need that much transfer speeds, okay, compared to, let's say, a GPU, it does not have that bandwidth. So you would use up typically 2 to 4 lanes of PCIe. And similarly for network cards, it depends how much bandwidth you have. For our Ethernet cards, you would use one or two lanes of PCIe. For let's say an HPC network, where you have very high bandwidth network cards like 100 gigabit per second or 200 gigabit per second, you would go as far as 8 or 16 lanes of PCIe. That way, you could send data parallelly or a serial bus. Um, and then you could let's say if the data is in fragments as well, then you can rearrange the data, reformat the data, and basically at the end point you get all the data in a chunk that is being transferred at a very very high speed. I think one of the fastest peripheral based system is the PCI is there, maybe just next to DDR or something. Um, Based on generation, the only thing I know about on generations, okay, every generation you literally double the speeds for a single lane of PCIe. So, for example, PCIe Gen 3, I think it was per lane was 100 or sorry, not 100, 1 or 2, yeah, 500 megabits per second to 1 gigabit per second, something along those lines. And for PCI Gen 4, it literally doubled to per lane being 1 gigabit per second, and for PCI Gen 5, you are again doubling the bandwidth per lane being around 2 gigabit per second. So I think that's how the generations work. The physical significance in terms of how exactly it increases per generation, I do not have much information about that, to be honest. So again, I think I already answered this thing where the PCI. Okay, I do not exactly remember the numbers, so I'll try to guess the approximate ones. So PCI Gen 3 was 500 megabits per second. I think so. For a single lane of PCI. Okay, and Gen 4 again it doubled, so it was 1 gigabits per second, and for Gen 5 it would be something on the ballpark of 2 gigabits per second per lane. So that's the bandwidth of the PCI lanes. In terms of any advanced features, I don't really think I have too much information about these things. I really do not have information about the speed modes like L0, L1, L2. Uh, Significance of power management, I do know that PCI lanes like the PCI physical connector that also includes the SM bus, um, basically the SM bus protocol. So you could um, like power off or keep place a device in sleep modes. So through that you can have power management. So yeah, but PCI does have um, like SM bus over it. So through that, so SM bus is nothing but let's say it's more of a superset of I2C. So yeah, through and SM bus is what's being used on the PC architecture for power management, as I understand.